All right, Kirchhoff's laws. Okay, we're going to talk about Kirchhoff's laws really quickly. So, a couple of these rules are really important for you to understand because they are followed in pretty much every circuit we look at. The junction rule states that at any junction, okay, total current going in or entering junction must equal total current leaving. Okay, so the total current that enters any junction must be the same as any current that also leaves that junction. You don't gain or lose any while you're in the junction. Okay, junctions don't cause you to gain or lose any current. Don't think that for a second that they will. Don't think that they will. That when you have a junction, you're not like bleeding any current or anything like that. It just doesn't make any sense. Okay. The junction rule, to elaborate more on it, is that every charge that enters a junction must leave. Okay. I mean, it makes sense, right? If you see 5 cars go into a tunnel, doesn't matter where they go from there, they should leave that tunnel at some point, right? It's the same kind of thing. If you have a bunch of charges that enter a junction, it would be natural to assume that you're going to get the same number spitting out of the junction, right? No charges appear or disappear at junctions. Okay. The junction rule is actually a statement of a principle that we call conservation of charge. We shouldn't be losing any charge at junctions, right? Doesn't make any sense. If they're not giving their energy to something, then then there's no reason for them to lose any charge or anything like that, right? The series rule we derive from the junction rule, right? So that if all elements are in series, so any elements that are in series, all elements in series with each other have same current. At same time. Okay, so if a bunch of elements are in series with each other, if you got a bunch of resistors in a straight line, they all have the same current because the current is the flow of the charges, right? It would only make sense that the flow of the charges isn't going to change, especially if they are just flowing through a straight line or the wire, right? It doesn't make sense to suddenly have a current here and then have less current later because where is it going, right? Okay. So here's an example talking about finding out the unknown current using the series rule and the junction rule, right? Every current that enters a junction must leave that junction. So we have here entering the junction is 3 amps and 2 amps and an unknown amount, and exiting is 6 amps, right? So the way that this would be set up is that 3 plus 2 plus question mark equals 6. What's question mark got to be? Oh, it's got to be 1. Okay, 1 amp. What about the second one? We've got 4 and 3 entering and then an unknown amount entering and then 1 left. Oh, wait a minute, that's kind of weird, huh? So this would be 4 plus 3 plus question mark equals 1. Okay, that doesn't make sense. So we'd have to use a negative number. And you can do that. You can have a negative current. A current is typically negative if it's flowing in the wrong direction, okay, or flowing in the opposite direction, okay? So this would be, let's see, so 4 plus 3 is 7, right? This would be negative 6, Okay, amps. Okay, that just means it's flowing in the opposite direction. So I guess it would actually be coming out of the junction. Okay. And then finally, we have this really weird looking thing, but the junction is actually right here in the circle, okay? So what's happening is that entering this junction, we've got 4 amps and 0.2 amps. Okay, so that's 0.6 amps coming in, and leaving is 0.7 because we have 0.6 and 0.1. So we actually need to add 0.1 amps into the bottom part here. Or we'd add it into there because there's a difference between the bottom part and the top part. Okay. This rule basically states, so we're going to talk about the loop rule, right? The loop rule basically states that when you travel around any single loop, around any single loop, okay, the sum of all potential differences should be 0. Okay, so when you're traveling around any single loop, right, the pizza shop analogy, nobody should be returning back to the pizza store with pizzas. We got to deliver all those pizzas, right? So when a charge is going through a circuit, right, it needs to be delivering all of its energy. Okay, the loop rule basically states that that when you go around any single loop in a circuit, you need to make sure that you're getting rid of all of your energy. This particularly applies to parallel circuits, okay? So to explain why this is, right? You know that voltage is the energy gained or lost by Coulomb, or is the energy gained or lost by each Coulomb. Okay. And the energy gained through a charge should all be delivered. Okay. The energy gained by a charge should all be delivered by the time it returns to battery. I guess by the time it returns to bat. Okay. Kirchhoff's loop rule is actually a statement of conservation of energy, right? Every piece, every amount of energy that's given out to charges should ultimately be given out to resistors. Okay, conservation of energy. And finally, we're going to talk about the parallel rule, which is related to the loop rule. Okay, and the parallel rule states that all elements parallel with each other all elements that are parallel with each other have same voltage at the same time. Okay, so if you have two resistors in parallel with each other, they should have the same voltage at the same time. Okay, let's do this last example really quickly. Okay, it's a loop rule example. We're using the junction rule and the loop rule together to find the unknown resistance capital R and the EMF epsilon in the rightmost battery. Okay, so first off, what we need to notice is that in the left branch, we have 2 amps in the left branch. So we would say that capital R and 16 volts have 2 amps in left branch. Okay. Meanwhile, in the right branch, epsilon and the 5 ohm resistor have 3 amps in left branch, or right branch, sorry. Okay. the middle branch, right, if the junction rule is to be followed, we should see that 2 is going to combine with 3 at this junction, and we're going to end up getting 5 amps going down, okay? Middle branch has 5 amps down, and that's junction rule, okay? Now, one thing to also notice, okay, is that we need to figure out the voltage drop across everything, okay? Well, we know that the voltage drop here, V equals IR, I is 3, R is 5, V is equal to 15 volts here, okay? Oh gosh. Okay. So we know that the 5 ohm resistor should have a 15 volt drop. Okay. Now, one thing that we need to figure out is how much voltage drop is there going to be through the middle resistor? Well, it's just V times R. That's going to be 10 volts, right? So 5 ohm resistor has voltage drop of 15 volts. Then 2 ohm resistor has voltage 10. Okay. Now, when we say voltage, we mean voltage drop, right? So we're losing that much energy every single time we pass one of those resistors. Okay. Now, again, loop rule, right? Take a look. If the loop rule is upheld, okay, which it most definitely is, then that means walking from the battery all the way around and back, okay, walking around the loop and all the way back would show us that we need to get rid of all of our voltage, right? So this essentially gives us an equation that is epsilon minus the 15 volts from the first resistor minus the 10 volts from the second resistor needs to end up being 0. Well, then what's epsilon got to be? Epsilon has got to be, it should be 25 volts, okay? Okay. Now, another thing that we can do on the left loop, right, is that we know that on the left loop, okay, left loop goes from this way all the way down, okay. One thing that we know for the left loop is that we start out at 16 volts, okay, we subtract an unknown amount, and then we subtract 10, and we're right back at 0, okay. So this question mark, this unknown one, should have a voltage of 6, okay? So this should be a voltage of 6, okay? Okay, that will help us abide by Kirchhoff's rules, okay? So we should have, and so we actually have accomplished the goal of the problem, or not quite yet, because we need to actually solve for R, right? And I've taught this triangle for Ohm's law, right? V equals IR, okay? And if we're trying to find the resistance of this one, we do V over R, or V over I, okay? And so V is 6, I, the current, is 2, so we should end up getting that capital R is equal to 3 ohms, okay? All right. That's all for that. Okay, I'll see you on the next one.